Welcome to this deep dive into building a custom reinforcement learning library entirely from scratch in C. Throughout this tutorial, you will construct an Autograd engine and implement the policy gradient reinforce algorithm without relying on any external machine learning frameworks. To put our custom library to the test, we will also code a complete snake game environment to train our AI agent and watch it learn how to navigate the grid.
Hi everyone, I hope you're doing good. In this video, we will going to implement reinforcement learning library from scratch in C. So I hope you have some understanding of the reinforcement learning, how the agent loop works and how the agent takes action in the environment, and environment gives the reward to the agent, and that how the agent learns and get feedback, and also have some understanding of the machine learning and stuff. So yeah, I think if you have all the prerequisites, then let's get started. I think this is a very good video because here we can actually go very deep and implement things from very scratch in C, and we will implement the policy gradient reinforce algorithm, and we will implement the model from scratch. We will implement the RL environment from scratch, and also we will not implement these things but also implement the Autograd engine, which is like a computational graph of the gradients, where that's how neural network trains. So yeah, let's get started. There's some of the things that I already defined, which is like base.h, which is like some types here which I have already defined, and this files contains some random numbers which will help us to use it in further video. So here's some things I want to mention first. Like, this is the video you can probably see in the screen. This video is really good video, and I think this person actually taught really good about like how to build the machine learning library from scratch. So this is kind of an inspiration that I took, and okay, let's go and implement the RL library from scratch. So yeah, if you want to check out this video, please check out that too, and pretty good video. So let's get started here. I think first we can let's define the Autograd, because that is one of the fundamentals right now, and then we can go for like defining model and then our RL environment. So let's get started. Autograd C. Okay, and here we have this what we need. So as you probably have the understanding of like how the model works, where you have like forward pass and then backward pass, so which requires a graph to go from one direction and then also in the reverse direction, and that graph is what we're going to be define here, like this, the Autograd, which computes the auto differentiation stuff in the backward pass. So here we will define the graph of the forward pass, and then in the backward pass, when we are going, that backward pass basically creates the traversal graph and identify variables within that, and then computes the gradients, and that's why we call it Autograd, which is like auto differentiation stuff. So yeah, let's go and define the variable first. Like, what is variable? Variable is basically the which is struct, it could be, and it will contains index u32 index, and then it will have the number of inputs, and that number of inputs will be like a number of, it's also a var, so inputs, because one variable can contains the inputs of it. So let's suppose I have a plus b equals to c, that c is also var, a is also var, b is also var. Variable is basically the parameter, you can say, in model. So this is what it is. It will have flags, u32 flags, and this var inputs basically will have number of inputs, and then it will also contain, so basically this var inputs is the number of inputs. It will contain basically the inputs. It can have like one input or two input. So because like for some of the operations like ReLU, softmax, we require just one input, but for the operations like addition, subtraction, that requires two inputs, which like could be A and B and any kind of variables. So yeah, I think what else we need? Like we need value, which is like a what, which will be a matrix. So here we will create a matrix. We haven't defined the matrix yet, so but we will define later. And a gradient. So gradient is also matrix, right? So these are the things. What else we need in a variable? Can you think of? Var can have like columns stuff. I guess not really, but a matrix can have, so we can define in the matrix. So yeah, we can define create matrix, which will have u32 rows, u32 columns, and and then it will have like a data, right? And that data could be 32. Okay, let's define first this thing. I will have this and then a data, I guess. So you can have like a u32 data, or I can say like f32. Yeah, we can now, this is like the actual definition, like the initialization of the stuff. We can define the definition here also, so it won't get confused that defined earlier or later. So type def, I hope it is recording. It is recording, I guess. Yes. So right, we can check it if this is working or not. Go to terminal, Autograd. So this is very confusing, you know, when we are using Python and C at the same time. u32 will come from, nice. Then we have like struct var type. So this is the var we have defined, but like, you know, we also need what is the type of this var, because it can have like addition var, it can have softmax var, it can have like different operational types of var. So with what type of var it is, so var type, and this can have like, this var type can have the types, which is basically shape. It can have var func shape. This shape, you know, this function basically will help in shaping this var type, and this var type can have like var func back forward function and backward function. So then it will have a good definition of var type, like what kind of function it has, what kind of backward function it has, and obviously the name. So it will have a name, right? And that is the var type, and also the type. So now we also need to define the function here, which is like this function and stuff, right? So after our definition of var, we can define, or like there's nothing needed for that, because like let's say here var b32 and function which will have like the b32 columns, b32 rows. This will have just var. Okay, now this is, we have defined, it will have forward, backward, shape, type and stuff. 4 errors, which is like type. This should be, I guess, this should be a pointer. Got it. The type will already be defined by the name here, so I guess that's it. And that also requires like how many inputs it has. This this var type will have. So we can also define like the 32 number of inputs, right? It is working. We can now, we need to define some of the definitions here, which is the var. It will have like var softmax, you know, that will have mem arena. okay, I haven't defined the mem arena, right? So what I'll just do is like, I will also include the arena thing, which is, arena is basically which defines the memory location allocation and stuff, and for this kind of projects. So I was just gonna go and so I've defined the arena here. This is the arena, so it will help us to actually create the arena and stuff. And arena.h will have all the definitions. So yeah, in Autograd we can just like import it like this. Now this softmax will have mem arena which asks for space and stuff, model state, model, and then var input, actually just input. I'll define the model state. So we will get the arena from the arena itself, and I'll define the model state, or we can define it first. It's not a great big deal. So struct model, and in this model we have, model state is actually model state. In this we'll have like, a lot of things which help us to build the model. The one of the things that I actually getting in my mind, which is advantages. So advantages require in reinforcement learning. So we will store the advantage here, and this is basically going to be float 32, right? And this is the advantage, and this contains a lot of things like number of vars, and number of vars will be again this u32, and it can also have a lot of different things, I guess. Model state, not models, it can have you, I guess that's it. We will innovate it later. I think we can just find what are exactly required for us. So this is the model state. We can define it here again, type def struct. Basically we can just define it here like that, var softmax, var arena state, model, var input. And we can copy it, right? For the var add, now this var a b, this again subtract. I guess we also need type of it, which is like the var type, I'm guessing. Var type subtraction is done. Now matmul, this is the matrix multiplication, and model state reinforce, and art. We'll get like a probabilities and RT stuff. So let's run this after this struct. Okay, nice. Now we also need like backward pass and forward pass thing. So void will basically, which is var softmax forward, which basically going to forward the softmax, and that require these things like mem arena and all the stuffs, inputs, and this will compute the, I guess this will compute the softmax and stuff. Yeah, so you don't need var type, you need this. And yeah, why we are just doing this is again going to be, same going for the backward. So void softmax backward, although like here we just need bar, don't need like, because we're not computing anything, we're just computing gradients, and we already have like the calculation stuff. So we are going backward, and then using this var we can just get the output of it, and we can compute the gradients. Got it. Var value backward, this is our backward pass functions and stuff. Now now we need to build function which can create variables. We have to find, this is some abstraction for us, this variable, Now we need to define variables, like create variables. So a variable will, a function that returns variable, create var arena model state, and view 32 rows, view 32 columns, right, and flags. Now in arena you will find like this push struct function, which is here, push struct function, which basically can be used to allocate the memory for the specific var first, right? So we will use this Autograd, I hope I'm recording. Yeah, all good. So this Autograd, this create var, basically first it will do is like var out equals to, this is how you define it, right? Like this, and this out index plus equals to 1 plus equals to 1, okay, plus I can say out, and then it will have, now we need to define, create a matrix. So matrix mat equals to create matrix, a function that can create matrix. Now before creating var, we should have created matrix, create matrix that contains like arena rows, columns, and the matrix is this, right? Rows, column, data. I guess like this is let me confirm, it will be a pointer, to be honest. Yeah, it will be a pointer. So yeah, I think this is this is how you define create matrix, and you basically going to push struct the matrix. This push struct will contain arena and that say out rows, out columns, return out. Data will be okay. So yeah, data, we can just like define data as push struct, just data is push array, because we already have this function push array, so we can use this arena tn. So array arena t is basically the matrix, size of matrix, and then rows and columns. Rows, we can just like push array based on like this. Yeah, exactly, that's how I use this. We can directly use this. It's getting confusing. So this working, we can try finding create matrix. We don't have arena, so create arena, create arena. Arena will take capacity, so let's define 1000 and arena 25. We can also print out the matrix, which is the matrix A, is it has 0 0 0 0. So this printed the first, okay, and we just print the rows u25. That's great. So this is this is here we are right now. Instead of like defining this, we can also say like push struct, and then it contains arena and then var, then create a matrix arena rows, columns, yeah, and we haven't defined the flags, right? We haven't defined the flags. So flags is something we can define here as enum flags, which has var flag none, which is 0, var requires have this value, binary flag. So these are the flags, like what exactly this variable have. Is it a variable that contains gradient, or is it this variable is a parameter, or like it's none or something like that, just used for computations? So that's what it is require, right? And yeah, I hope it is recording, my voice is clear, and yeah, so this is what So we are here right now. Define the matrix, and then mat will have, this will have a name value, and then out val equals to val out grad equals to, if it has a, if I would say type def enum flags, it's just defining as u32. Let's say if flags, if it is a var flag require cat, then probably we also need to add gradient into it. So create metrics arena columns. That's it. I think inside this var there's nothing more else. There's inputs. So for that, like, I guess we also need to define the inputs. 0 equals to a equals to b, and it will only happen that if out dot number of inputs contain greater than 1, then you have to basically store it there. And this number of inputs comes from type number of inputs contains them at this. We also need to add type here, which we will get from var type, and we will also, I guess, like, model state is not required here, so just remove this. And we can also remove, I guess, like, when we are creating var, like, first time we will create, so we will not have like inputs, and we cannot define this. So I guess earlier version was better, which is like model state and this thing, and type we can say null. Let's say this. Yeah, that's it. Now we can just return the var. We will define like the inputs and stuff when we will create a node, so out we have defined, and type, because we haven't defined in here, should be like this is working, I guess. And then we have to define node. This creates the var, and we can actually go and then try to create it. We can just go and var b is a var, create var arena, then model state is state. I don't know, like, why did we needed a model state here. State model flags will be like 0, I would say. So yeah, it's working. Does it have a grad? Oh, it won't have a grad, because like we have to find this. Well, this model state that I just remembered, like, it will have a number of vars. So when we create this thing, that's why we need model state, because in index we can say it number of, this will have an index, right? This will have an index. So number of var model number of vars plus means, like, as we create this var, that will also reflect in model, which is like a model will have, it will actually automatically goes inside the model, and then it increments the number of vars. Although, like, this limits the possibilities, like if you want to create number of vars outside the model, then, but yeah, I think for now it's good. So var create var, this is done, this is working. And then when we have to create a node, what does node will do? Node basically the nodes of graph, because we have graph from bottom to, like, operations like softmax. This is itself is a node, this itself is a node, this is a node, this is a node. So as the computational graph grows, it will create a node based on that. So that's why, like, we need to create a node, and for that, like, we have to define graph, which is like, again, a struct graph, and this graph will contain this graph contain the variables. So because graph contains like a nodes, we can say like a nodes, but like instead we say like vars. and that var is a pointer, the array of pointers. So you can say like also this double asterisk is the pointer to the location of pointers, so this will have bars, and it will have a size. What is the size of the graph? That's it. This is the graph, and matrix in the graph. What exactly is happening here? Why it is failing? Did I did something? Okay, I just did something here crazy, which is okay because the model wise is null. So model, like it's just definition is wrong, but yeah, I think number of bars will be going to a plus plus in this. I'll take a little break, I guess. I should take a little break, or like I should go create something really. Okay, so graph has no problem with this, and okay, now this is done. The graph is like we have defined a graph. Now node, that node basically will give us the var itself, create node, and that contains var a and var b, and because a node itself is a softmax, let's suppose, so it can contain var a and var b, and it can have like a model state, it can have flags, 32 flags. That's it. So if inputs, and it will have like a type var type, and this type will be basically a point. So this will create a node, create a var. This var basically arena and stuff will have like the var a and var b. Don't need model state var, and then okay, got it. Now this var type, if type is type equals to var will have like type equals to type if. Now that this type contains, this type contains shape, so, and that shape is basically can have a b, can have a and b. We have seen it like that function contains a and b, a b columns and rows, a b. If this is basically returns true because it's a this shape, this var func type is a boolean itself. So if this thing contains, if it is true, then that means that the shape is right of a and b compatible enough with the operation, whatever the operation based on the type. And if it is true, then I guess like we can just move forward with that. So I have just to do is like var type shape, and before that I think I have to define rows equals to 0, rows columns equals to 0, and then we have to provide the reference of it, and that will have the things. But what we will do inside of this is like create a node and then model state. I guess like that's why like models was required here. This is the right way to creating a new variable based. This is based on this. The goal of this create node is that to create a new variable, and but that variable is already coming from something, so variable a and variable b, so that's why like it's not like independent variable like this. So but I guess like we don't have to do that because this is already doing inside this create var, that requires model. That's why like model rows, column, and flags. We are making complicated a lot with this because so a lot of things we are actually taking here which is not required. So if the goal of this node is to create a new variable based on the past a and b, so we don't need like a lot of information. We already have some information from a and b. So I guess like we just remove this thing. Now as arena we have model state variable b and this type only. Now this flag we can just define, we do flags as var flag none first, right? And then if flag if a isn't equals to null and a flags and require grad, or b isn't equals to null and b flag and var flag requires grad. So if this condition is true, like means like a has this, either a has like the gradient on or b has this gradient on, then we can say like flag is requires grad. It requires only one of it because we are using or here. So this is how we can get like flag. And for the rows and columns, yeah, we have defined it here, rows and columns, and then inside this, if this is not true, if this type dot shape is not true, then we can just return null. And after that we can like create this var because now we have rows and columns. So this shape will, I haven't defined the shape function, but this shape will do some kind of like manipulation with this rows and columns. That's why like we are passing the reference. So it will change the whole this rows and columns, and then we will provide here. So we don't need to pass from the arguments. We're already getting it by because a and b, is this new variable is coming out from a and b. So either it is exactly their shape or like some kind of matrix multiplication they are doing. So we can already compute like the out shape. We can compute the rows and columns of the out shape. So this and then flags, right? Arena model rows, columns, and flag. And then var type is type. We can define it like this. We already had defined it, isn't it? Okay, now so we can also define this because it is coming out of a and b. So a and b are basically the inputs of this. So if var inputs 0 is basically a, and if var dot type number of inputs greater than 1, var inputs to b. That's it. This will create the node. We will return the awesome. This is great. 4 errors, which is like a flag. It should be flags. Okay, it should be flags. Yeah, it should be flags. Columns and rows. It should rows and columns, I guess. This wasn't the error. Incompatible pointer to integer conversion using U32 star. What does it mean here? Which is they should have is working. I guess I should take a little break and then we can just come back and start it. Okay, so this is great. Next we have to implement the graph. So basically how we going to build the graph is we can build the graph using the output. So let's suppose the first is input and the last is output. So output could be like after the softmax, and in between there's a matrix multiplication, ReLU, and all these layers. But softmax is basically going to be the last layers, and that softmax we can put at outvar, and then outvar that will back propagate and discover the nodes, and then eventually going to figure out. So I can just show you, like I basically like this is slides I made. Yeah, like this is the graph. Like this will have inputs. Matmul, I think it's visible, right? This input, matmul, add, activation, stop. So this is like the forward pass, but during the gradient computation stuff, it will going to be a little different because uh, we need to go backward. So we will provide the output var and then it will discover the inputs because we are storing the inputs also. So it will go to all inputs and then discover everything and then finds out like, okay, which finds out the dependency of the inputs and then compute the gradients. And yeah, I think that's we have to do. Now for that, I guess there's this thing called create graph, return graph, and it will have output. So there's this algorithm called depth-wise traversal algorithm, which will take the one node and then finds out the inputs node and then traverse back. So it will have like a stack. So it will have a stack, and in that stack we can put a lot of different things. So it's like this. Stack will have some, we will put a lot of things, more like A, B, C, D, E, all these computations, and but it is going in the forward direction. Sorry, it's going in the from backward direction. So because we want to create this graph, we will probably, what we will do, we will go out and using output graph, we will, okay, let me explain again. Like, so in stack we have this a lot of computation, A, B, C, and D, and all the stuff, right? So these computation basically will have from backward. So we are going from outward, which is like outvar, to the inputs. So this will go into the from outvar, which like the outvar will be here, and then it will discover the inputs which dependent on the out. So that why like it is not in the right order. So we want in the right order for the graph to execute the forward pass, and so there will be two kind of these things, and this will be one is stack and other will be out, which will have all the in the right order, whatever the right order will be. So the first it will contain leaves first and then contains all the output and stuff. I can explain you better if I have ChatGPT asked about like to create the computational graph, so you can look at those graph. Let me just pull this thing. So yeah, so let's suppose like you have this graph z is the output, and then you will traverse back to discover some of the inputs. So z is dependent on x and y, okay, and then x is dependent on a and b, and y is dependent on b and c. So you will see like you probably find that okay, when you go in this direction, you will check the inputs to y, okay, and then you will add in the stack, you will add z in the stack, y in the stack, and then add c and b in the stack, and then check another input x, then b and c. So you will actually create stack like this from backward. But the problem here is like there's a lot of problems with this, which is like here you can see like this y is also dependent on b, and x is also dependent on b. So if you just like go in one order and then discover the inputs, then you will basically going to have basically add this b twice. So you will have two b's. So you have to make sure that okay, you are not adding the same parameter, same variable, and you are also adding these variables in the right order. So then we can actually create the graph, create a graph. So yeah, I think this is what we want to do here, right? Now to create this graph, like first we need to define some of the things, which is like graph and this graph is empty here. And some of the variables like stack, that stack is honestly the pointers of point locate. It is a pointer to locate points the location of pointers, the stack, and this malloc size of var model number of vars, and same as out. And then visited, because we have to check like we are not adding the same variable twice. So visited will be p32 boolean visited this will have this will also be a pointer, and just like this. And then basically, you know, stack will have this initial stack will contain stack size equals to 0, and out size equals to 0. stack size plus equals to stack size plus equals to out var. Okay, so this will contains the out var, and then we will traverse back, you know, via. So I hope you understood this, like, which is this is a post increment thing. So it is exactly like this, stack size. So initially it will get the value of like 0th index stack, and 0th index we are storing the out var, and then stack size increasing after that. So stack size will become 1. While stack size is greater than 0, what we have to do is like we have to go and then pop out the stack. So var current and stack size, this will pop the index. So this is a pre-increment, so it will turn to 0 and then it will index. So this current is stack minus stack size. Then what will happen, that we have popped out the stack size is 0, it has 0 length, but we can actually see if this current dot if this index, if this visited current dot index, if it is visited, then just add in the output, you know, add in the output out. Don't go further, just continue, because like we already, so as we have seen, like, okay, if it already visited this kind of a thing, then just add into the out size and continue. Otherwise, like, just go and do more computation, which will be like just discover more input. So let's suppose what we are trying to say is like, you know, if you have not visited this thing, you discover more inputs. And if you already visited this variable, okay, don't discover this. Okay, we will add this thing into the output. I hope you're getting. I know this is not kind of makes sense, but like when we actually run this create graph, you can actually understand. We will see like what exactly it's doing through the output. So if visited current index out size plus current continue, and then we have this for use 32 I equals to 0 less than input size. So we have to like find out like the inputs, which is the if type is not null dot type will have number of inputs, otherwise 0. So if it is inputs I less than inputs I plus input is okay. So if this input is less than the input is, we have to like iterate for u32 j equals to 0, j less than stack. It will make sense, like I'll explain what I'm trying to do here. I j equal, if it is like equals to, that means like it is like a duplicated. So because like as we have seen, like x also had this b variable, y also had this b variable dependent on, so both shared the same variable. So we need to make sure that okay, one is only added. So first when we discovered x, we will add the b. Now when we discovered y's variable, the variable of y, we can actually update b. We can replace the stack. Let's suppose like this, it will add x, y, b. Let's suppose like this, b and a, right? So again, when it finds that z, now in next iteration, like if it finds like y is also dependent on b, b, so this condition matches. Okay, this is actually already in the stack, right? This is already in the stack. So it will what we need to do is like remove the old position thing, just have this in the here. So it will basically remove the old thing and then have this in the right order. So only one b is going to be there. That's what we will going to do. It is already there. How we can remove this is basically we can shift the order. So let's suppose when we discovered this, this is here, so we can just remove this and shift the order. So how we can like do this is basically we will just go iterate k equals to j. So we have discovered this at the jth position, so we'll start with the j, and j will go to the stack size -1 and k plus plus, and this will what will happen, that stack of k equals to stack k plus 1, right? So the k plus 1 position will become the kth position. So yeah, and then here we can just do this stack size minus. So one position, like because one position is already shifted to the left, so reducing the stack size also, and that's it. What else is needed? Like we haven't stored the inputs. So this was the input, right? And stack size plus plus equals to nice. That's it. Like this is the graph. So it will run this traversal until the stack size is not less than 0, and pop the last thing in the stack, and finds out if it's already visited. If it's not, then continue here. If it's visited already, just add into the out stack, and this input is basically will discover the number of inputs, and then I iterate over the inputs, and then after iterating the inputs, just check like whether we have already added this in the graph in the stack. If it's not if it's already added, then reorder the position and then remove the last one. So kind of a graph it will have, and we can see like we can print it. That will give a better idea. So first let me define the model state. I don't know like why it is not getting initialized in the right way. I guess okay, this is done. To be honest, like I wanted to check like this thing, but we haven't like defined the model yet. Like, so we need to first define the model, and then we can use that model to define a model state. Let's define the model. Let's see. I'm gonna basically copy some of the things here, just the imports, because imports is like difficult to manage stuff in C. And yeah, to include base, arena, mat. We don't have anything in mat, I guess. You can define the mat dot c mat. Okay, nice. This should be just defined somewhere else also. Okay, so everything because of this, it should point the input is coming from the current, so not from here to. So here we can define like the Actor-Critic model, which is this will give us model actor model, because we are going to use reinforce only, not PPO and stuff right now, which I thought to actually also implement this, but probably this was going to a lot long. So yeah, let's go with like actor model only. It's like simple, not too much in this. We don't have a value function in here, which is great. But it will be very high variance. So make sure like when we were going to train, we'll see like a very high variance, and it will train in a very long time. So yeah, I think create actor model, model state model. It will have, you know, the weights and stuff. So var input arena, I guess model, the input will be, so we are going to create some kind of, we can create a graph later on. So when we have like a model state defined, what we can do right now, like, and we can finish this function, which is these things. So you have actually just noticed that it requires a var type, you know. So for that var type, I'm going to define the var type here, which is var softmax, which will have number of inputs equals to 1 dot name equals to softmax. And I hope like it's the right syntax. Number of inputs, shape will be, okay, we haven't defined the shape, you know, so there will be two functions actually, which is var b32, which is like boolean, and var shape. This will contain the var a, b, and call. We will check if in this implementation I'm not checking too much thing, making it simpler. So we'll only check like if a isn't equals to a dot rows isn't equals to b rows, or a columns isn't equals to b columns, return false, because this is the same shape thing. You know, the function, the goal we are trying to achieve with this function is that it should have a same shape, and this same shape will going to have also update the rows and columns, because these rows and columns here, you can see like when we are creating the node, we are calling this shape thing and we are passing the reference. So this will change the rows and columns here, which is defined as 0 0, so it will change to the right column and stuff. So this we will dereference this, and we will update this as a rows, and similar to like var a b 2. Now in the matrix multiplication, it's kind of a different. So if a rows isn't equals to a columns isn't equals to b columns. Oh, my alarm is, when did I have alarm? I did have alarm? Like I didn't know like I had alarm. I guess always had skipped. This is the first time I'm discovering. Anyway, it's 5:30 a.m. right now happening though. So if a columns isn't equals to b columns, and so it should have like this kind of because in matrix multiplication you basically compare with like the first dimension of the matrix, last dimension of the first matrix, and the second dimension of the first matrix. If it compatible with this, then it can only do the matrix multiplication, otherwise it can no. So return false, and dereference this rows, and change the parameter will be a rows, and columns will be b columns. This is it. Now yeah, we can pass these things into here. don't. I hope like I'm defining kind of the same. I have to check. And then forward function, which is going to be, you know, softmax forward function, and dot backward function will be softmax backward function. Okay, and we can define the same thing with other also var value equals to dot name. Although let's check like if it compiles. Wow, because it is giving errors, because the thing is that it is a var, you know, so it will have val. Okay, it is defined here, so we can do also. This should be void. Wait, this should not be void. Okay, so I guess like the error is basically because of the signature is not matching with this. It is because the var softmax. Wow. Okay, so I found it, like what exactly the error is. You know, so this is just a definition right now. We can define it. Not coming right now. So this is good. Now what we can do, we can here define these functions, you know. We can put information inside this function. Where softmax forward, this will basically do the softmax operation. So, you know, softmax operation, we can just define it here. 42, which is what is softmax operation if you just think of it. For u32 inputs, right? We'll have inputs, and so we can actually define size. So u64 size equals to, you know, and iterate and compute the softmax. So I've already like did some define the actual thing, like which is, this is softmax, and this is the formula. Really, this is this, and policy gradient like 3 and 4, this is it. So you probably have familiar with this, I guess. And then what we're gonna just do is like we will iterate over this z to collect the zi, and then compute each of the with each of this element. And similar to all those goes, you know, this size will come from var columns, and then go to size I plus plus. You know, if now what we have to do is like, okay, we have gone into this size now, because if you check this formula, I hope I'm recording this. If you check this formula, you're basically doing the max of z. So first data, which is like a max, let's say 32 f32. Okay, and then we can do this should be the output of it. So I guess like we have to define it the right way. Input is the data, which is the I will store the formula. I check it was the, I guess, the max value. Like this, we have to just do the sum, and then we can divide this with the thing, right? This is the thing we have to do. Var val, and this is only for max value, and then we have to do the sum, because you know, we also have the sum, and then we will divide it with the we'll scale this later, but like let's compute the sum first, and then we will. Okay, let me explain this again. I guess you haven't really got what exactly I'm saying. To compute this softmax forward, what we need to do is like, you know, we have to compute these formula, and it's simple. It's not really difficult. So because we have this var, we can get actually the inputs. So like this u30, we can calculate the size, which is the var val columns, and multiply by var val rows. Although like this is not a matmul operation, so I'm just like doing val. I'm just resting on the val, otherwise like I can take this from input as well. So for 32 I 0 I go size I plus plus. Now, because if you see this, it's basically like we have to compute this in element wise, where the Euler has the power of like zi minus max of z, and then it is normalized with some summation. Although this is exactly the same, like this equation and this equation is same, it's just like it is summed over it. So the easy way to do is like you basically I less than 0, you do max value, max f32, max value is, let's initialize with this var inputs 0 is also a var, right? Input is also a var. I forgot that, like input is also a var. So we'll have a data. Now this max value going to be changed because like we need to find the max value. It can have max value on like this thing. Now again go for like size I plus plus and the sum, you know, so sum will be to do sum, and which is this function which is we are trying to do is, and what is the function name? It's xf, you know, the xf, and it will basically, if it just, and zi is basically, you know, is the input. So this we're going to store in where? This we're going to store in var val data I. And so the upper part is done. Like this will also compute the upper part, and then with the sum we can compute this, and then we can actually divide it, you know. So how we can divide it? Divide with the sum. So go with the u32 I equals to 0, I size plus plus, then that's it. This is our softmax. This is our softmax, and exactly this is going to be for the ReLU also, that you have the size, then you iterate it over it, and in this iteration, I hope like I'm audible to, yeah, in this iteration we can just like go and then see what exactly is happening, like because ReLU is basically turning all the negative thing to 0 and then all the positive thing to whatever the value they have, right? So if the data, if the var dot inputs of 0, it will also have the only one input which is 0, val data I is less than 0, then var input var val data I equals to 0. Else if it's not like this, var val equals to inputs, whatever the input is we will just store there, and it should be inputs. Now for the add operation, add operation is good, it's not very complicated. So again the size will be this, and in this size we can just say, you know, if val data I equals to var inputs 0th val data I plus var inputs 0 val data I should be 1. So it will have element wise addition, right? The same goes with the sub also, if we just going to subtract it here. Now matmul is kind of very different because it will have, you know, a lot of things which could be a transpose, non-transpose and stuff. So for this one, like we will define another set of function. Okay, so the matmul is kind of different here because it will have a transpose and different kind of stuff. So what I can do here is like, no, here we can define another set of things which is matrix. This matrix multiplication, we will have, we are not going to take anything out from the function because this actually means no transpose in either side of it. So it will basically going to, yeah, I guess like we don't need this kind of a thing. Void, because we are passing the out matrix and matrix A, matrix B, right? And for do I equals to 0, I less than size I plus plus. Basically this this A, how we can compute the size, which is, we don't need to like to go in the same way like how we went through in the last add and softmax thing, but rather we can go this and then u32 j equals j less than matrix A, 2 columns, and then A plus plus for 2, we can say I64 because maybe matrix is bigger, very k equals to, we need 3 iteration because the first is the out rows, and then we are going indexing on the actual matrix A, which will help us, the second iteration will help us to indexing on A and B, right? And the out, which is again going to less than these 3 indexing, which can help us to do the whole thing. Now I'm going to explain again. So void mat mul nn, this nn is basically the not transpose, so to have this out matrix out matrix A matrix B, and if basically we can just u64 I equals to 0, we are just using u64 here. Maybe like matrix is very big, although like it doesn't make sense why we use only u32 in earlier version, but it's okay. Earlier version means in softmax, so really we could also use the u64. It will go to the A rows columns, A out rows out plus I plus plus, so out to the rows plus again j equals to 0, j less than columns j plus plus for k equals to 0, k less than, it is k 0, k less than out columns k plus plus. So basically these 3 iteration we are going to do to actually index the matrix. So if you don't know, like the matrix is basically just the how we index things, because we are not using like any kind of array, we are just like indexing through the actual memory. So if you think of this as a matrix, then 1 2 3 4 5 6 7 8 9, this is a matrix. Row, if you want to access the memory, the location of this matrix, the row major, you basically mostly use row major basically, and how you also store in the memory of the matrix, which is the row major majority of the time, which is like your flattened memory will be 1 2 3 4 5 6 7 like this. It will be like this. And the column major will be if you want to store with the column major, it will be like 1 5 9 13 like this, 1 5 9 13 2 6 10 like this. So here we are using like a row major thing. So it has a formula to access do the indexing basically, which is like column plus rows number of columns multiplied by number of columns. So row multiplied by number of columns will happen first, and then you just add with the column. This is exactly like telling you have this matrix M and then row and column, and like probably you have used this in Python, which is like slicing. this is row and column, right? So this is how you actually store these things. Otherwise, right now we're going to use this formula, which is column row. So here's a twist. Let's suppose if we want to transpose, because if you know more about transpose, if you don't know, transpose is like changing this row to column. So this will become column and row, and then so this thing will also change. So this will become row and column, right? So this will change it. Now when this will change, we can able to define functions like with if you want to multiply with transpose or not transpose. So we can also change the formula and use the right formula indexing thing, right? So transpose, and basically it is exactly like A transpose. If you do A transpose on I on K, it is exactly like A of K and I. So here the out of data will be I plus K, I plus K. So sorry, I plus J, J plus I. Sorry if I just say J plus I, because J is the column and row should be here, because if we are using this column plus rows multiply by number of columns. So Ji then columns equals to, you have this out data, and which is K plus I, which is, so here you can see like K is 0 and I is 0 in the first index, and then you just, and if it's 0, then basically this whole thing cancels out and you're left with like a K. So K is become like a column for you here, and row is 0. So here's like K is something that I able gonna index over it, and you're going to do the dot product with B. The B dot product will happen with the J and K. That's it. Like, this is the whole formula. This is the thing. Now the cool part is that you can just change the indexing. Let me check like if it is correct. Yeah, it is actually correct. Now this map n can be like nt, which is like a transpose the P metric. So you just have to do, what you have to just do is like, you have to just change this order, just I plus K, so if you just change the order, sorry, I guess like I changed the A of it, which should be the here K plus J, then P is transpose. Now if you want to transpose this T and N, then basically A should be transpose. So if A is transpose, so the iteration we are doing over the K over the A, sorry, will become rows here. So, and this will also change I plus K. Why it will become rows? Because it is transposing things. The A is transposing, because right now we were actually moving over the A, we're using A to iterate, but like A wasn't changing, B was changing. So our iteration loop was exactly like this, but like right now our A is affected, which we were using in the iteration. We can also use the B, so that will create a non-effect thing, but like right now it's good that we are using only A for the iteration. But as A changes, A is getting transposed, so we have to also change the iteration loops. Okay, so and then we can have like a TT, which is like both are changed. So now it will become I plus K, K plus J, and then will also become like rows. Now we can just like define the final maximal, which is like a case of it, matrix A and matrix B. Now this will basically and okay, So this is like just a 0 0. If all are 0, then we will use this NN1, and if anyone is true, we can use this thing. So we can define like case thing, like, you know, there's one more thing like we can also say, which is 0 out, if you want to do the 0 out, although like it's not very important. And then we can just get rid of both, because like if both are true, then it's already going to be TT. So 0 out will help us to basically initialize the metrics with all 0. So if 0 out, so I initialize with for u64, and transpose A or transpose B. If it is kind of a situation, then switch, and then I can just copy this case that going to be okay. This is this. Now we can utilize the same macmul here. We can say, let me just check if we haven't made any mistake. Yeah, everything looks fine. Let me just fix this quickly, these errors. Let's implement this reinforce forward, which will be the computation of the log and the returns, right? It will be the logs and the returns. So the log of probabilities basically will be, I can just copy from here, size, right? And in that, basically what we can do is to make it more safer, because we will get like a probability from the inputs. So max of either inputs 0, 1. This is the max, or basically do the 1 will be the returns. This is reinforce forward. Okay, now we have to compute the backward passes and stuff. So backward passes, the gradient we have to compute, and it's very simple. Also, like, it's not difficult. I have already added what will be the loss. So you can see, like, in the for the reinforced loss, the gradient will be like GI times the RI, which is the reward here, divided by PI and negative. So, and really for really it is X. If it is greater than 0, then TI, it's like the previous gradient, or the evaluation gradient of value, or if it will be going to 0. And then softmax gradient will be this. So yeah, I think let's compute this. First we can compute the reinforce gradient. Can do like this, and if I guess this should be 64 to only use 64, and then over it, and grad will be GI is basically the grad. We can also do similar kind of thing here as well, what we have done there, because I think, you know, if and wire, if this is like this, you know, in the input, this is getting very confused, you know. But the thing is that I want the prob should be the gradient, you know. So input will have this 0th index as a probability, you know. So val, I can say crap, I guess this is something like this. I think, you know, it's basically a transpose. So if when you do matrix multiplication, it will going to transpose. So for the gradients, you know, I will do much better if I can just do it like this, A and B, and we have to compute the gradients of A and B. So here you have seen, like, we haven't computed the gradients of inputs 2, because with input 2 is basically RT, which is the minus R, it's like reward here. So we don't need like to compute the gradient of return. It is just a weightage, so we can just leave it, and then we can only compute the gradients of the probability, which is the probability of given action and state. Probability taking action given state. So if variable this flag a, we can just say a flags, then we can do match. We can pass the inputs 0 b. Transpose will be, because it's a, so transpose b will be transpose here. To calculate the gradient for the a, having the gradient of a will be basically going to be the transpose of ab. So ab transpose b transpose, and this here a is transpose and b. I hope you're getting it. So yeah, for the addition, it is basically the addition. Yeah, now we have to do the same thing, which is like addition, and put the entire thing in here. It will be not just like plus equals to, but rather okay, here we have just did some kind of mistake, which is it will be grad. No, it is fine. Okay, so some errors which I will solve here. 394, this is for the a, and same goes for the b. So b, it will be, this b is going to be 1 1, and that's it, right? Like for the subtraction, I think for the subtraction it is also kind of a similar, I guess it's very similar, because but here it will going to be negative. We can change this to, now again, like this input equals to only one input. Okay, and size will be, this size is this size is and in this input, what we're gonna do is like if equals to 0 is greater than 0, this, otherwise this. That's it. Yeah, I can also add one more thing, which is like a floating point, right? And it's going to be plus equals to. Okay, now we only have left this softmax. So the easiest part about this is that the vector from this is our equation, which is like a dot product of g and s. S is basically the softmax data, and g minus g is the gradient of the var, and g minus g multiply g dot product with this, and then softmax data, again the dot product. So let's compute this dot product. I'm going to take this, and also going to take this. I will say dot, because we want to use the softmax data. This is the dot product it will do. Now again we have to do it, but this time data dot product of dot s g minus s. Okay, so I hope the computation is right. Okay, we have implemented everything now, like all the things which we have defined as a function. So the next what we have to do is like we can start building our model, because we have built all the things required to build a model. So we can start building model, and for that, like this model.c. Okay, so we have implemented this Autograd thing. Now let's create environment, or we can create model, but I think I want to create environment first. So environment C is this. The here we probably gonna do is create some struct and enums. So let's first understand what kind of environment we are trying to create. We will create a snake game environment. I think this is going to be a really simple one, and this which can actually have some level of difficulty also, which have reward structure where the snake will get reward, and if it hits the wall it will get penalty and stuff. So this will going to be simple snake simple environment. So let's go, this can have like actions, action left will be 0, right will be 1, up 2 down 3, right? This is going to be action. Now snake env, this will contain a lot of information like state, which has a state variable type. So this state variable type will be struct, right? And this state is not state snake, state food, what will be the state of food, and score will be f32 score, and action will be POV, like what exactly the point of view, because snake can point, because in snake game you probably have seen like snake has a point of view, it goes in one direction, and then if we in keyboard, like in keyboard phone, when you press the low button, down button, then its POV changes and then it moves in downward. So something like this, it's basically the point of view of the snake. Now this is the action POV, and then what will have POV, that's it I think. What else we can have? Thus current state will be snake state, food, then score, this, yeah. And then we have like this type def struct. I hope it's recording, I guess. Yeah, it's recording. Type def struct env. Then we have a replay buffer, because in reinforcement learning you probably have like heard of this kind of a replay buffer where you do the gradient accumulation later after doing the rollouts. So you do the rollouts, so I can explain it like this. You do the rollouts, you do the rollout is basically collection of data, you do the rollouts, and then after doing the rollouts you do the gradient step using that rollout. So you collect the experience. So that's why like RL is basically doesn't require training data, because it generates the training data, the pure RL thing. So this will generate the data, the experience from the snake, and then we will use this experience to correct the agent's action. So we need to store these experience. That's what we call like replay buffer struct. This replay buffer, will have a lot of things. Also, this snake game will have like a rows and columns, and grid size, and action POV, and number of steps it had took. So use 64 steps. This replay buffer will have, the first is like trajectories, and this trajectory is itself a struct. So let's suppose the buffer size is 512. Okay, and episode length, because episode length is basically snake is collecting the states and actions in a single game. So it goes to x0 y0, like coordinates x1 y1. So basically navigating the environment. So how many steps it is taking in a game is called episode length, because it cannot like take forever. We have to like, it can take forever, it can just like take until it's win or lose, but like let's define a definite steps. So it could be like 200, right? Or maybe like we can define more. Let's go with like 100, right? And this can be 1024. Now this trajectory, this trajectory contains a lot of information, which is like state, episode length, its states, which is like all the states the snake went through, and this food, states, episode length, action, so then all the action it took, and action, what is the POV, episode length, rewards and returns, F2 returns, and state, next state, because we have to store the what next state it went through, what was the next state after taking the action, and next states, and done's, like is the game done, do we have a result of it? So not, then we can actually iterate again and again and again. So this is some kind of abstraction layer. In trajectory we can say 32 count, right? And here we can also say length. Now this is the abstraction, define, dude, what exactly is this error? Just ask the chat why we are getting this error. Now the error will go away. Now create the env. So this basically create env will take because we are not like defining this in arena, like it's very array kind of thing. So here, like in trajectory and all stuff, we haven't used any kind of a pointer thing, but that's okay. I guess like let's go with grid size. Rows will be two side because the grid will be a square, so we can just like qrtf and grid size, right? And this q32 calls equals to side, same thing. Then this will have like a columns and rows, and then we can define like snake take the push struct, which is the arena itself, and size and all stuff. So we're gonna go like there's other ways which is like malloc, you know, we can just say size of this thing, size of env, but like let's go with like arena, and now 25 or 36. Let's go with like 36 size. Okay, let's create the env, and then we can define stuff here, you know, snake.x equals to 0. That's how we can define env.0, and action pov, right? So because it's starting from 0 0, so 0 0 will be like top left, bottom left, and then in the x and y graph, so 0 0 will be like a top bottom left, and then it can POV towards the right. So this will define the env. We can actually print the or print. Okay, why we were doing this? Damn, what exactly is this? It should be 0, right? I think it should be 0. I guess like, you know, we have defined in a wrong way. We can define like this, which is much better. Just do malloc like this. Why it is getting like this long value wrong with this? Damn it. When we are returning env, bro, that's it. Small mistakes. Okay, so now this is done. We have created the env. This is our env, and we need to find the, you know, we need to reset the state also. So after episode end, we need to reset it. Reset again, like this, going to be like this, but we can make more interesting here, which is like get random lock. So this will give you the random food location based on the number provided, which could be so I'm not doing any checks here, so just to make it simple, but you can just think like, okay, there will be a check which checks the range within the range of like grid size and rows and columns. So if there is function random in the prng this file, which is this function, define it like this. This will be I32 because this can be negative. Yeah, so that's why define this side here. Why doesn't got it, and same here. Now okay, so this reset in env is done again. You know, you can see bypassing it, we are getting random. Now taking action, we need to make sure that we are taking the right action in the environment, the valid action. So we have to define that, you know, action. This will basically snake game env action. There will be one more action, you know. Okay, that's it, I guess. There can be one more action, like which could be none, like no action. Okay, and take action. If env dot action, if action equals to right, no, action equals to none. Action, if action is none, then action will become, POV. env is POV, like, because we are not taking, the model decided to not take any action, so the POV, the whatever the POV of the snake will become its action, so just take action, push snake in the POV direction, because snake will going to take action at every time step with its POV. What the model had to do is to take action to prevent it from hitting the wall, or like to get in the direction of food. So if action is none, this action is right, env x will be, snake will be, snake dot x will be plus 1. I guess we are in the, okay, so this is the, and then in the end it changed the env POV to action, whatever the action was. Okay, that's it. In the else we can return action is right, the snake position will become, should be 1, nice, 1, and if it's left then it should be -1, and if it's up should be, the y should be, okay, y, it's been a lot of time. So yeah, so this is working, right? What we need, we need to build some sort of vector, which is some sort of vector in the sense, because you have this inputs and manual and stuff like that. So this input will be like some kind of embeddings and some one hot coded vector which has all the information about the snake world or snake env, because we don't have any kind of like input like text or something like that, but this snake env world which has a lot of information, like where the snake is going, what's POV, what's the state and all stuff. It's actually a lot of information, so we will provide this as input to the model, and model will actually find patterns and observe it and produce an output based on that. But we need to convert this input in a right way so the model can actually understand it. So the best way to do so is to create some kind of vector, right? So build state vector, which contains some informations like, which has like metrics and state, and then state of, this will be state of snake, and food, and action, what will be the POV, what is POV of the action, and columns in, right? Now to compute the snake I, we know the formula of this column row in row major thing. So in a grid size, like we are storing, let's suppose this is the state, it will have like for 0s 0 0 0 0 0 0 0 0, and then for like grid size till the 36th of this thing length, or I can say 35th, because if we have like 36 grid size, we have like this kind of a state, and snake I will be 1 here and 1, like if the x and y is like this. So this will have some kind of information in a flat vector, and we can do the same with the snake, with the food also, snake position, it's like a one hot encoded thing. And then for the POV, we can, for the POV, it can have again some kind of a similar vector which can actually have some information. Well, we are going to create a very simple vector, not very like kind of a embedding type dimensional thing. So just a one hot code which has some information which can actually help the model to observe it. Use snake I, which is this columns plus rows. Rows is basically u32, snake, columns will be snake dot y, right? And multiply by, and then plus. It's a little bit weird, I would say, but you can define it like this. X state.y. It's kind of different here, but like it's okay. Columns is x. Sorry, I'm just got confused in this. State.x and then plus state snake.y, then multiply with columns. This is the right thing. Exactly with the food. And then we can store in the metrics which we have here, which is the input metrics, data snake I, let's do snake 1 0. So whatever the index of the snake I will have like a 1.0 floating point, and in data food I size plus 0f. This is a flat vector which have like a, in Python or like in other matrices, in NumPy we actually see shape like this, where we have this three inputs and then the grid size. But here we have flattened thing, right? So 3 into grid size. So this is exactly our input vector. There will be like another function which will help us to find the rewards, because we have defined the take action, but we haven't defined the reward function which help us to get the reward. So when the agent will take action in this, let's suppose if it finds the food and finds the food of the state, then we have to give them a reward. And if it hits the wall, then we have to give them a negative reward. So right, so this will give reward, and it will have snake. Now if env.x.snake.x greater than less than 0, or env.snake.y less than 0, or env, if it is like this, then give them a negative reward or something like that, right? Or env snake.x is greater than the env rows, or we could say 2i32, and if it's like greater than the env, then it's like we should give it a reward f32, give them basically minus 5, okay, 510f. Now if it lands on the food, if snake.x equals to env.food.x, and env.snake.y equals to food.y, then reward, give them reward like plus 10.f. These are the two things basically. Now it is done. Like it will get the positive reward here, but like now we have to, when it eats the food, when it actually lands on the food, we have to give them a new location to this food. So that's why like new food will be, we'll do while new food equals to state get location and then close, okay. And if new food.x equals to env snake.x, and means like if we don't want like where the position of the snake is, we don't want the food should be again come at this position. So we'll just like, okay, if this is the condition is true, then run again iteration and find new food and new location. That's it. I guess. And yeah, have record and then turn reward. All done. We can actually train this simulation, this environment. We can simulate this environment and train the model. We haven't defined the model yet, but it's okay, like we will define later. So here we can actually create a training pipeline. Training pipeline will be simple also, it won't have much there. Like, in training pipeline we have this training of RL, and in training of RL you basically do rollouts, collect experience, you will compute the returns of the rollout, and buffer, and then sample experience from the buffer, and then train it. This is the whole pipeline of the RL training, you know. So void train arena, I guess like there's no arena, model state, model, and snake env, anv, mem arena. There's arena. I don't know why we need arena. We need to create here, but okay. The first thing we have to do is, like, you know, we'll do the forward pass, and we haven't defined the forward pass, you know, because rollout will do the forward pass and stuff. Well, I will just, you know, for the ease of this, what I will just gonna do is, like, I will paste this epochs, rollout size, episode length, and gamma, which will help us to basically, these are the hyperparameters. And let's see if it's compiling. Okay, we'll see this later. Here we need to do is like forward pass, right, and backward pass, right. This forward pass is basically will have arena, I guess. Arena, no, this forward pass will have, you know, graph. Now u32 is the size of the graph. Dot, this will be a pointer, and then u32 I equals to 0, I less than size, I plus plus f. Now iterate the iterate the size. What else we need from here is access the var, because, you know, the graph will have that build graph we had here. Create graph, this will give us the graph from the forward pass, and we can use this to write where it went. So we have to iterate over this compute the vars location, right? Dot type parent dot type, which is like it itself is a var, and if it doesn't have a type is equals to null, return. Otherwise, just to, because it will have a forward function type, and this forward function, you know, will need a var, which is again yeah, that's it. This is the forward pass. For the backward pass, you know, it will be exactly kind of similar to this, but if this is not true, then what you have to do is like continue, and if you have to continue again, and if it is like a var require grad, as if it's a parameter which a var require grad, then we need to clear this thing, it's grad, so this will clear the gradients. So clear the gradients, and then you can use fill. I guess fill is there. Then fill the graph -1. The last variable should be 1.0f, right? So fill the last variable, last variable's gradient to 1.0, and then traverse back basically. I32, I64 0 less than I should be graph, and I greater 0, I minus. So traverse back, and then, you know, var and check if it has gradient, then, you know, current equals to 0, then continue. If current dot type isn't equals to null, and current dot type backward isn't equals to null, we can change to current, because like we already defined CR. Okay, so it's good. We have implemented the backward pass. It is not defined. You know, why fill is not defined, because copy this. There's some function we can actually import. We can define in which basically fills and fill the random. We don't need this random thing. Okay, it is compiling. Then in the arena, or in the env, we can go and train it. We play buffer So we will do like a rollout experience collection. So 32 I epoch equals to 0, epoch goes to epochs, epoch plus plus, right? And then in this epoch, we probably will do forward pass. How we can do forward pass from the model, because we have model, right? So, but I guess, in here, model state, when we have defined, it has only these things. So it will have forward graph, via graph, output. These are the things a model state will have. Again, go for j equals to 0, I less than rollout size, I plus plus. This will do rollout. Now we need to take a step in the environment. So let's generate an action. First, let's see like if it is working or not. So we can call train model state. So this training function is working, right? Then what we have to do is roll out sizes, and then in here you can say model dot forward graph is equals to build create graph. And the create graph, what the create graph will take: arena, model state, and outvar. The outvar will be, and the backward graph will be order output. This will be a cost. That's why like we need to define a cost here. It is null, so it will probably will give this auto graph, return a pointer of graph, and this is not done yet. We have defined this graph as this. I guess we can change the definition of the model state, that we don't need this. And this will graph dot, because we are actually adding in the out of it here, out. So the graph dot vars will be out. Now the graph dot vars is basically not defined yet. Push struct, or basically we can do, there's this another thing which is push array int. It will save some memory of it, but basically just not initialize this array like others. Like you can see, it is true means like it initializes everything with 0, but it doesn't. So yeah, var graph of vars isn't equals to null, means it has a space allocation. Graph dot vars equals to graph dot equals to dot number of vars equals to out size, and then we can just do mem cpy to move the variables locations pointers to here from out, and size of will be, and then we can just free the stack because it was a temporary location which visited. It's not number of hours. So the issue is issue was coming from here, this kind of an issue, because we were defined after this and using here, so that will resolve the issue. And okay, so this is done. Now what else we need here? We haven't defined these functions, so var softmax, which basically creates the variable of softmax. So we already have this create node, so there's not really needed for any kind of logic. You just need to call these functions, right? So we need to call this return it, and this takes up some input, which is arena, model state, variables. Okay, that's it. And then var type, a and b is basically input, null, var type. We have defined it, right? We haven't defined that thing. We haven't defined the var type, really. Oh wow, we have defined the var, this thing. And relu, for the relu dot number of inputs equals to 1 dot shape equals to var same dot forward u time. It will be exactly like this. sub. This will be mat. Two inputs var shape mat forward audible. Yes. What is this error? Var type softmax. You can find this. Let me search like why exactly I'm getting this error. Okay, it's again like the same issue. I have to put this in here. This is a big issue. So what I will just gonna do, I'll just define definition here, so it will be better. No, it will not gonna work, I guess, because it's static. So okay, we can complete this. Now type. This one is relu. This is nice. So we were completing our training pipeline, and this we probably take the action. So let's suppose the action for right now, let's take the action of this thing, print of action plus this is the action, and this action is okay. This is working. I would say we have like a 5 action, 1 2 3 4 5, right? So it should be 5. Why sometimes it fails, I just don't know, but it's okay. Like, we have this action and take action, and this is the env action we can provide. After taking the action, x will be like taking this thing. If it does not take action, then oh, got it. It can happen because is game over. What we need to do is like void e32 game over env snake.x less than 0 or it's exactly the same. It is working right now much better way, but okay, so if this is true, then okay, yeah, it's working. And when it gets -1, it is it. Yeah, when it gets -1, the game is over, right? See, I'm going, because it is like it's been so long and we haven't finished yet, so I'm going to take this so fast, and let's go finish this. Okay, this is how the game will over, and every time we have to reset the state. For every rollout size we have to take this thing, and for the trajectory, define a trajectory, which is a buffer, and this buffer, it's coming from here, and this has I. Okay, now we can store it inside this trajectory the information. 32 I go to episode length. Okay, length is I already defined, but it's okay. I plus plus. Now in this inside this we will take the action. Now we have state equals to env state food state. Okay, action pov is env pov. Now we need to build the state vector, and inside this input model val. I hope it will work, I guess, because val is null. State and pov env columns env rows, like this. If we're going to fail because we don't have a model, right? So what I will gonna do, like I will quickly I will just gonna copy and paste the model, because I have a model is simple. It's nothing here. So these are the things it has. create Actor-Critic model, which is basically arena, and it will take a model. And this is input, and we are creating a var of size like 76 in one, because 36 is grid size, and again 36 is for the hour storing the food position, and 4 is for storing the POV. So this is 76 1 var flag none. Actually we have 5 actions, but like eventually the actions becomes 4, because if it is non-action, then we are actually defining it. You can see here action equals to EN. So yeah, even if it's action none, we are actually changing the action, so it becomes 4 action. That's why like 76 is the byte. We have to add one more. So this weight 0 is, we are creating var create for this 128 76. It's 178 size. And bias, this is the bias, and we are providing the flag of it, which is it's a parameter and also a require grad true. For the input, it's require grad none. Basically, it doesn't need to have gradients, and it's not a parameter also, it's just an input. So, and then we have this weight 1 and bias 1, weight 2 and bias 2 with like 128 128 hidden dimensions, and the bias will have 128 one dimension. Okay, and then here we are initializing this with like fill rand and all stuff, which we had already defined, I guess, or if not, then I think we have to define it here, and we can import stuff here. Okay, yeah, just note this. That's why like it is. So let me just like think like what exactly is the error. Okay, so the error is gone, but I have to change a lot of things because the code I pasted was different what we have created. So like a different kind of function name and like parameters required for that. So yeah, I think now we don't have any error. So yeah, I think this is weights bias. We created like 3 weights and 3 bias corresponding to that, and then this basically randomly initialize these things, and it will initialize the layers. And z not a is basically the matmul of weight and input, and then we are adding var add. Using var add, we are adding this thing z not a and b not. So that's why like we created this var matmul, var add, var relu, which basically creates the nodes, and then it will not going to compute right now, it will create a nodes that what are the operations required. Okay, so it will create each node like this, and then similar to that we have another matrix multiplication with weight 1, and the input is a naught, which is the previous output. It is exactly like PyTorch we do in Python, but like we are basically doing more scratch way, and can see layers in front of it. So Z1B is basically the bias, again just added with Z1A and B1, and then this is the relu layer after to normalize this thing, and then for the again doing the matrix multiplication with the last weights, and then doing the addition var add, and then we are basically doing the computing the probabilities using var softmax, and defining a model output equals to output. Okay, and advantage is basically it's actually none right now, like it doesn't have anything, just create a var and it does not have any information, but we will add the information inside the advantage during the training. And this cost is basically the reinforce loss we have. So var reinforce, and then basically it will have like a var type reinforce, and output and advantage it will have. Then the cost function is this, right? Now here we can now say create actor model, arena model. Now this will work. Okay, so there's something which is basically doing some sort of, we can use coding agent, I guess, to otherwise it will take a lot of time. So we can just say like, okay, what exactly is, okay, so these are basically the errors, which is like null, but we have created the model, isn't it? Okay, number of bars equals to 0, because number of bars are basically kind of this condition we can actually have to secure the model. Okay, we have allocated more memory. Now let's see. Okay, but this is okay, I got it. That was mistake. Okay, so the major issue was basically here, as I was like very confused on like, maybe like we needed 77 dimension because like we had 5 actions. So I thought like, no, okay, it's only 4, I guess, because like action is taken, but it is actually going to be 77. That was making the issue here, and now it is actually working fine. And yeah, this will be cost graph. Now if you just run the training, okay, build the state, and now let's finish this quickly. We have this arena env.c. There's this, we can sample the action using our probability distribution right now, but let's not focus on that. Let's build the pipeline first. Take the action, we can take the action. Now we need to store all these things. So if for this we have to like have to reward at reward, or this thing is reward. Now this give function, we are getting here reward, then we can actually env score plus equals to reward, right? And then done will be captured like here, and then next state is basically env snake after the action. The previous state was the like this, then trajectory, we can actually copy this and it will actually store all the information, states, food states, POV, actions, reward, and all stuff. This will store the informations. There's no rewards, there's no rewards. Okay, there should be a rewards. Yeah, you can say it. There's ST because it's trajectory we are iterating over. Done is actually there's still more errors. Trajectory. Now this rollout is done. After this rollout is done. What we can do is like we can compute the returns. Like, because what exactly the returns of each thing? Returns that it's going trajectory of 0 to episode length, and we will compute the returns, which returns is the sum of all the rewards at each step in a trajectory. So I guess like this is buffer.count. It's not a very efficient way to do so, but like it's okay. So this trajectory gain the buffer trees f32gg is basically return 0.0f or 32. So in advantages you basically go from trajectory length to 0 and then computes the trajectory the returns at each step. So t equals to trajectory rewards of t plus gamma returns of t. I can basically paste this algorithm. This will go to trajectory and computes the using gamma. Gamma is basically used for is a discount factor, and then trajectory returns is g, and then sum return sum. We haven't defined any kind of return sum here, but like, so we don't need this return sum, return square sum. Yeah, it is used for like that standard deviation calculation. Sample count, that is also not needed. Average return, well, we can actually define this thing f32 average return, which will be outside of this. Let's print this. We also have to add this in our buffer. We are getting returns, which is like a negative. So our snake game, basically snake is getting killed every time. I don't think I can find any positive here. Can you find any positive? I don't think. Okay, this is good. What else we need? We have computed the returns. Now it's time to compute the gradients and all stuff, which is like actual training thing, isn't it? So we will going to go again and backward pass. In that backward pass, we have computed this thing, which is clearing the gradient. Clear the gradient. So again, like we will do this. Before computing the gradients, we have to clear it. So 32i equals to 0. I will go to graph dot size I plus plus, and then there's no model dot graph. Okay, this is clearing the gradient. Now what we need to do is, like, again, this is a training phase. In this training phase, what we need to do is like just go through all the buffer count is basically the rollout size. So u32i equals to u32, and then go to the trajectory. This is the trajectory iteration, but here instead of episode length we will go trajectory dot length. Okay, and again build this vector, and this time the state is coming from trajectory dot state, no, states of I, and trajectory state t trajectory. Now this is done. What we need to do is, like, again clear the advantages. So for u32 I k equals to 0, k less than the model dot advantages. This will go to the we just want to, like, because we will compute the advantage, so just get rid of like the old advantages thing. So advantage, now to compute the advantage, it's simple. Advantage is basically trajectory returns of t minus the baseline. The baseline is basically the return mean and some. Okay, this is basically the return mean. How can we compute this? We can compute this average return. We can not average return, we can just say due to return mean. Okay, and average return is kind of, so for the return mean I can like, there was this sample, 32 samples, number of samples 0, and return sum. Average return is basically something else. You can just like remove the average return here and put this inside this. So number of samples, in a trajectory, and return sum plus equals to g. That's it. And then after that, number of return sum f32 return mean is sum is sample number of samples. So this is our advantage, and yeah, this is our advantage. Then we can just model advantage equals to advantage, right? This advantage is basically val trajectory actions. Okay, that makes more sense because so there will be 5 actions, so 5 index for it, but like it will only store whatever the action it took. So it will only store the advantage on the whatever the action it was. So actions. Now just do the forward pass with given the model dot forward graph, and then do the backward pass given the model backward pass. Cost graph, actually. Awesome. This is actually computing the gradients. And now after doing this, after computing this, optimizer step. You have to do the optimizer step. Gradient scale is learning rate divided by 32 samples count. Right. Now what we have just done here, I have to do the same thing, and inside this the gradient current data will be into gradient scale. This will take the gradient step. Well, this will just the gradient scale, but we need to also subtract this, so it will also going to subtract this and subtract current val width. Inside this, the out matrix will be current val width, current gradient. Sub will be not defined, I guess, because sub is where it is in the Autograd. You can say like this. This is actually working now, and this is the whole implementation of the reinforcement learning from scratch in C. And I know probably I have made some of the mistakes here, like implementing in live some of the few things probably, although like the library is pretty big, what I actually built, but it's a very minimal implementation of it, where I just try to get rid of a lot of functions and try to attend everything in a single file. Like it's going 400-500 lines codes in some files, so I try to attend in everything, not try to manage everything, not try to check the safety checks and all the stuff. So it was like a very minimal implementation, try to simplify this, and I hope this made sense. So I guess like probably I don't like this will learn, but it will going to learn probably. Like if you just like leave it for like 20-30 minutes, it can find. So you can see right now it has started getting positive rewards after I adjusted some of the things and improved logging system and stuff. So you can see like the returns are like positive. Earlier it was negative, negative, then started learning and iterating, and then become better. So reinforce is a very like unstable algorithm, you can say, because it has a very high standard deviation, but still it can learn. It can perform really good when you actually train for longer time and can figure it out. So yeah, I think this was about the reinforce algorithm in this video. I thought to actually implement also more like more algorithms like PPO and the versions of PPO and stuff, but I guess like this video is going very long, so I'll cover this in next few videos or like in any other project. But see you next time. Bye.